when, okay, I should have gotten some tuition on this first. Which button brings it down? This on. Okay, that works. As usual, I worried I didn't have anything to say, and when preparing, of course, this morning, I realized I may not be able to say enough to really give a complete picture of what's happening. So the title was Group Actions on Linear Categories. And the subtitle would be Mirror Symmetry and Langland's Duality. But it's something like a bit of a 2D, 3D theory. So not what was very fashionable recently with the work of Kapustin and Witten on geometric Langlands. I should also mention that I've given some talks in Utrecht last month on the same topic, and the slides are linked from my web page. So because there's no paper describing this story, that will be at least provide some sort of reference. Right, so let me give some prehistory and then explain what's been happening. So in about 2008, I think in Bonn, I gave a first lecture along on this topic where I tried to explain that the statement along the lines that the B model mirror of BG is a space of conjugacy classes. And G is a compact Lie group. And the left-hand side should be written, so that means A model of BG should be mirrored to somehow B model on the conjugacy class on the group, meaning that, say, gauge-Gromov-Witten theory should be described in terms of something having to do with conjugacy classes. And two objections were raised to that proposal from the audience. There was an example to justify this, of course. Two objections were raised, and then they ended up being correct, and I think overcoming them actually was much more interesting than I thought. Objection number one was that mirror symmetry usually has two sides, AB and BA. So what's a BA statement? And at the time I had to say I have no idea. Now I can say I understand it completely for a torus, and I have an idea for an abelian groups for what the other direction is. And objection number two is, where was the Langland's dual? Where is G check the Langland's dual group? And that was less clear at the time. That was a valid objection. I mean, it came from the fact that people want to see Langland's dual groups everywhere. But it was less clear it was an objection because the key example, which is still the one which makes the theory well defined, so key computations, some key computations, use a twisted version of the A model of mirror symmetry. So use a twist by invariant quadratic form. On the Lie algebra of the group. And once you choose that, it becomes very hard to tell the difference between the group and the dual group, especially if you just all you see is the Cartan algebra and the Weil group, then you really can't tell the difference anymore. And one flaw of all the examples I had was that it's impossible to tell which ones come up. But now, after thinking a bit more, I'd have to say the objection was correct, even though I was skeptical of it at first, and indeed the correct statement involves the Langlands dual group. So let me try the correct statement now. So a corrected statement, or improved statement. It wasn't wrong what I said. The part that was detectable was indistinguishable. So improved statement is that mirror symmetry interchanges Bg with, let's say, a variant of the space of conjugacy classes in the Langlands dual group, so G by conjugation, the conjugacy classes. And it works both ways, so A to B is pretty precise. I hope I can explain that today. B to A is precise for a torus. And in general, I'll have to say it's open. But the statement is precise enough that we can tell now that really you have to choose this or not some other construction of things you can choose from the Langlands dual group, from the group itself. So in fact, there's something else which comes up in the process of trying to construct something mirror symmetry, which might be mistaken for something other than the Langlands dual group, but in fact, when you look more carefully, you'll find that you need it. So let me say a little bit about, first of all, what this sort of thing means. First of all, so what does it mean? So it's not just saying that you're going to take Bg as a space or as a stack and construct its mirror, because that's not only what we're after. That would be sort of gauge theory for a point. And I like that example very much, but that's not enough. What you want to be able to do, you want to be able to let G act on any space and construct a gauge version of, say, the A model topological field theory for that space, and say that the mirror of the space, the mirror B model, can be coupled to the conjugacy class in the dual group. And conversely, if you let G, so let me write that actually. So, okay, works. So let's say G acts by Hamiltonian. So let's see, Hamiltonian G action on the symplectic manifold X omega should give rise to, let me write should and I'll make it precise, to gauge Gromov-Witten theory and then the statement of the mirror statement above must be interpreted so I should have said there at the bottom for those that take notes that the objections were correct. And can be fixed, can be addressed. So here, if you have a Hamiltonian G action, a symplectic manifold, you'd like to say it's a gauged version of a Gromov-Witten invariant as a TQFT, and that should be equivalent to a TQFT constructed from the mirror by coupling it in some way, the conjugacy classes. And this should be equivalent to coupling the mirror of X mirrors the x check of x to the space of conjugacy classes. Conjugation. And same for BA. I did not think enough about BA for B to A. And let me just say a word about what the gauge-Römov-Witten theory is, because that's where we make contact with computations. So gauge-Römov-Witten theory. So it's going to look at the moduli of triples, actually. Sigma, let's say P and S, where sigma is a Riemann surface, well, stable. Actually, sigma is going to be, let's say, a semi-stable Riemann surface. P over sigma G bundle, G C bundle, and S a section of the associate X bundle. So S is in gamma over sigma of P cross over G with X, holomorphic stable section. So this is, of course, going to be a stack. So before you can integrate over it, you have to stabilize. So need to stabilize, need stability conditions, not in this modern sense, but in the old-fashioned GIT sense. Need GIT stability conditions to integrate. And there are basically two of them, two sources for them. One of them is, well, you have to construct an ample line bundle, and there are two obvious semi-positive ones. Namely, there is a theta line bundle, or powers of it, on the moduli of G bundles, on bund G. So this forgets a section X, just looks at curves and principal bundles on them, and for that there is something which plays the role of a polarization. And then there is sort of a polarization pulled back from the space X, assuming it came, the symplectic form came from a line bundle. So polarization from X. So you have basically two sources, and you can weigh them in different ways. So
when you think the trade-off for that, is it over G or over GC?
P is GC, that's over GC, I guess. And then you're going to ask if X is symplectic. What does that mean? Let's not get in. Let's not go there. Yes. No, you want the associate X bundle, yes. So if I had said the more obvious thing, which would be a unitary G bundle and the section, I would have already committed myself to one of the two limits I'm about to describe. So can linear combinations, linear combos of these will define versions of gauge-Römov-Witten theory. And there are two extremes, of course, when you use just one of them or just the other. People call them adiabatic limits, because then you don't actually have positive line bundles. You're at the border of positive line bundles. So the extreme cases where case one, you just declare the underlying bundle is stable. The underlying bundle is stable. And of course, you're having a bit of trouble when you have semi-stable bundles that aren't stable. And then you're looking at the moduli of pairs of stable bundles together with stable sections of the associated bundle. That's going to be a compact space, so you can integrate over it. And the other extreme case is when you kind of ignore the bundle story, but you just force to use the polarization coming from X, which will, in some sense, expect it to. There are theorems that effect to force you to land inside a semi-stable locus for the G action on X, and then you're supposed to get the Römov-Witten theory of the GIT quotient, of the symplectic quotient. So this guy is meant to appear as a limit of gauge-Dromov-Witten theory. And this polarization is easy to describe. This is related to what I had mentioned before, the Casimir twist. In GW theory. Yeah, it's called a theta line bundle because for GL, well, for GL1, it is a theta line bundle. But bun G, modular of G bundle. So on, which is the set of pairs of sigma and p. So I forget the section. And the polarization from X, I was a bit careless. So morally, what you do, for every point on the curve, you pull back the line bundle on X by evaluation and take the continuous tensor product of those. In other words, you take the cohomology of the resulting bundle and its determinant. That's the way to do it.
So when you say bun G, both sigma and p are invariant.
Yes. I guess bun G over the more universal curve. I don't know.
So it's sort of an infinite type kind of stat.
Yeah, but it's infinite because of the bundle, not because of the curve, right? The curve is going to be. Well,
No, but
yeah.
you only require a curve to be pre-stable. So curve.
Well, it's required. You have to be a bit more careful at the nodes. You want it to be stabilized by something, basically. So, basically, if you have bubbles where the bundle is trivial, you want to collapse those. You want to enforce that sort of equivalence relation. But I mean, yes, I mean you have a. Your question is very relevant to defining this over nodal curves. In fact, at that point, there's a choice, and gets me too much into a parenthesis. But yes, I mean, the part I will talk about will not see that choice at all. There's a reason. It's because I will talk only about the categorical level, Fukaya category versus coherent category, and that part of the story does not see the compactification of moduli space. I mean, in other words, from the category alone, you cannot construct Gromov-Witten theory over mg bar. You can only construct it over mg, and there's extra information required to extend it to the boundary. There's just, it's not a bug, it's a feature. I mean, it's a bug, of course, but it's unfixable at the moment because general theory does not provide a canonical way to do that. The theorem, which has been announced by Kontsevich a long time ago, and there is still no precise written up version of it. I know some versions of it. I could make precise, but says that somehow the Frobenius manifold, which means the genus zero theory, plus the category, the Calabi-Yau category, together with the compatibility condition, together determine the Gromov-Witten theory over mg bar. So some of the boundary data comes from genus zero, and the bulk data comes from the category. That's roughly. In toy models, you can make some versions of it precise that I know. So since I'll only be talking about the categories, it means we will not encounter the question, which is very difficult maybe not difficult, but certainly involved, of understanding the stack of bundles over nodal curves and sections over it.
For the sake of actually having a definition, can you explain it a bit how one integrates using these two integrals?
Well, you use that to define, well, you use a combination of these to define a moduli space which ends up being compact.
Okay, you're not going to define it, of course.
I'm not going to define anything, but yes. One of them is kind of obvious, right? At least even a situation where semi-stable bundles are stable, this universal bundle, then you have a compact base, which is a moduli of bundles, and then you look at sections, stable sections give you a compact space. So that limiting case, if you like, is obvious. But even in that case, if you run into bundles, semi-stable bundles which are unstable, the compactification becomes a little laborious. But so in algebraic geometry, I think only for GL1 there's a proof of what? There's a proof of completeness, I think, of the stack. and more or less it's believed that compactness of the moduli space follows. In the non-abelian case, there are other symplectic methods that allow one to define compact moduli spaces, but they also take the two ingredients here in a different form. I mean, they usually, well, I'm still on page 1, and I'm completely getting away from where I was going. But at least that's the place one is meant to make contact with reality, and the only place where in the computation, the toy examples I can give you, the only place where I can make contact with reality will be essentially a case where the symplectic quotient is a point, because that's where one can really understand gromov witten theory without having to worry about compactification. Then one can compute two sides and find a match. But, all right. So since this is what we're trying to do, to allow an arbitrary x, point I was trying to make is it's not enough to say define something like a Fukaya category of BG and some sort of category of coherent B model on that side and show an equivalence. What we actually want is an equivalence. It's a two-categorical statement. Equivalence between, say, categories with A model G action so it's like A models over BG, or gauged A models, and category is coupled in some way to a conjugacy classes. It's actually not exactly this space that comes in except for the torus, and we'll have to change that. So it's really an equivalence of two categories between such things. Right. And I'm assuming we've linearized everything, we've linearized the Fukaya category. So now at least maybe the connection between the subtitle and the title becomes apparent. We want to study this kind of thing and describe it in terms of that. So we want to say that categories with an A model G action, which I have to define, must be presented equivalently as something that's coupled the category of coherent sheaves on the space of conjugacy classes of the two. That's what you must be able to state if you want to gauge mirror symmetry.
What is a linear category? Do you mean the home?
This would be this would be the Fukaya category. Oh, sorry. I'm sorry. I was too fast, but you're right. Linear category is a very good question. Thank you. Not assuming the space of objects is linear. The home spaces are linear. Are vector spaces, or more realistically, perhaps differential grade vector spaces. And composition, of course, is bilinear. I mean, if you worry, the example would be the Fukaya category, which is A infinity, but general nonsense tells you that if you work over complex coefficients, you can actually find a DG replacement that should have all the properties, you want the same properties. With a G action, it's a little shakier, but it's believed to be true. I have to define first what G action is. So also linear categories. And for a torus, there'll be a very precise statement exactly like that. So for G, we'll have to, for a non-abelian group, we'll have to work to get to something making the Lagrange dual appear. But, okay, so first let's define what that means, category with G action of any sort. And then after we define that, we know there's a meaning to this. And then we'll see why we expect something like Lagrange duality per sure. So this is part 2, which is preliminaries. There's various kinds of G actions. Any questions about part 1? I'm not going to, I hope I'll get to give an example maybe of this, but I'm not going to discuss any more the issues or difficulties that come up in defining the Gromov-Witten theory. So we're not coming back to that. Okay. So the easy case, G is a finite group. What does it mean that G acts on C? Definition is that G acts on C. On C means that for each G in G, I define a linear endofunctor. I always forget this one, phi sub 1. I want it to actually be the identity. And for any pair GH, there's a condition. There's more data. There is an associator, alpha GH, giving an isomorphism of functor from phi G composed with phi H to phi sub GH. If I was acting on a vector space, this would be a condition. Now it's data. So this is data, data, and the condition comes later. The condition is the associativity condition. This is called the associator. The condition is, well, if you have three group elements, there is a square you can draw and have better commute. So you can go from phi G composed, phi H composed with phi K in two ways to phi sub GHK. So we can compose first this way, or we can compose the other way, G composed with phi HK. And there's an alpha. I'm not going to write them out everywhere. There's a commutation condition, and it looks like a co-cycle type condition on alpha. So let's see an example. I'm not sure. I don't think there's anything else we can ask, actually. Right. So two isomorphisms of functors, they either are equal or they're not. That's where the condition comes in. The condition comes in when there's nothing else to say except two things are equal or not. If we're working in a two category, there will be one more set of data and the condition will come next. Because at that point, you can only tell whether two things are equal or not. It's sort of, when you reach this true and false stage, at that point you have a condition. Before, you have to give data. Okay, let's do some examples that are somewhat enlightening. So example, the category, let it be a category of vector spaces, and let phi be the trivial action. So phi G is, before the example, I want one more definitions. Put down definitions. Definition, the fixed point category, CG, has as objects tuples consisting of an object in the category and isomorphism for each group element from X to phi G of X such that there's a condition. blah, blah, blah. When you compose the phi g's and you compose the capital phi g's with respect to the alpha, something commutes. Let me just say such that something commutes, exercise to write it down. There's only one obvious thing to write down. And morphisms, so hom CG between two objects, x say phi and y psi, is sitting inside hom C of xy, and the condition is commute with all the data, commutation with phi psi. Whenever you can write something that could commute, it has to commute. I'm not going to use it much, but it's good to know. There exists a quotient category and define C sub G, quotient cat. And if C is a very special, simple example of a category, it's category one object and endomorphism of that object, of course, will form an algebra, so the category is essentially an algebra in that case. If C is this, then CG becomes a cross-product algebra. So it's a generalization of the cross-product to actions on categories I'm not going to write. And the reason why this is useful, so useful because, this guy is useful because, a little lemma, you can show that if you take the category of A modules and take G fixed points, you get the same as G cross A modules. That already covers the next example. C is vect. Phi is trivial. So phi is the identity always. And the associator is 1. That's a trivial action of any group on vect. And then the fixed point category, exercised by the definition, is a category of representation of G. C is vect, let's call it sub alpha. Phi is the identity. Alpha GH from G cross G to C star is a group 2 cocycle. So you check that the condition on alpha translates in this case to the group 2 cocycle condition. Then vect alpha fixed point category is, there's only one thing you could write, defined from the data, which is a projective representations, rep alpha of G, the alpha projective representations. They're actually both secretly contained in this example of fixed points and A modules. So this is C mod, of course, right? This is C mod. And rep G is, of course, modules over the group here. So okay, so the point is, just as defining an action, there's on the category is more data. When the fixed point categories, you can actually get more information. The fixed point category is actually rich, more interesting than the original in this case. So it's not true that the subspace of a line is a line or zero when you move into representations on categories. The fixed subspace on a line vect is now a vector space of rank dimension of the group, the number of representations, reducibles. Okay, so what's the final thing we need? Because I want to talk about Lie groups. What about structure on G, on C? On G and C. And structure could be algebraic, holomorphic, C infinity or topological or so on. And the answer, well, morally is you ask Grothendieck. If you do that, he might tell you to get lost. But of course, you can read what he did a long time ago. He taught us how to do such things by encoding structure in terms of functors. So instead of trying to put structure on the objects in the category and trace it down in the definition of the maps, you replace, to choose a site, a Grothendieck topos, for example, the category of analytic space or algebraic varieties or C infinity spaces maps, and convert C to a sheaf of categories and G to a sheaf of groups. That's the obvious one usually. And then you just say that the sheaf G acts on the sheaf of categories C by repeating what I had said before. So this acts on that. Repeat the definition. So this one is obvious. Usually you know which group you want. This is where the work is, kind of deciding how to put the structure on C. So that, for example, if C was coherent sheaves on a variety of scheme X, so C is a coherent sheaves on X, and the reasonable functor is functor to use sends the test scheme U into the coherent sheaves on U cross X. So I'll not say any more about what it means to have a smooth action or a continuous action or a holomorphic action or of course this is covering up a lot of possible structure. Oh, yes. Which we do need because let me make another technical remark. There exists a model structure on the category of sheaves of categories, sheaves of cats on a topos. I should put quasi-categories here because the technical definition, which allows one to derive functors. So for example, the functor of sections of a sheaf of categories over a space can be derived. You can talk about the cohomology of a sheaf of categories over a space, which is going to be a quasi-category or maybe a DG category. It has to be in some world that allows a bit of homotopical information like chain complexes. E.g. R gamma over a space X on the over a sheaf of categories, and you can define, and that with some care it works, can define the fixed point category, a derived fixed point category, the derived fixed point category, which you need in the DG case, as R gamma over the stack BG of the sheaf of categories. If you have a sheaf of categories with a G action, you can enhance that to a sheaf of categories of a stack BG in your topos, and you can derive the functor of global section, and you talk about a derived fixed point category. Computing it is a different matter, but at least it's defined. In the case I talked about before, if you're over a field of characteristics 0, which I didn't say, but that's probably fine no matter what, then there is no derived. There are no derived functors of that. All right, and now we get to the point of distinguishing between different kinds of actions on categories. We could say we want the A model action, the B model type action. And what I describe would be the B model action. So for the A model action, there are versions, so two versions for Lie group actions on a category, on a cat. They can be infinitesimally trivial. And I should really say trivialized, but philosophical. That means trivialized on the Lie algebra, or on the formal group, if you prefer. There is a formal group at 1. Or they can be locally trivial. And that means, in words, that infinitesimal action, infinitesimal trivialization is integrable. And this is a type of action which comes up for Hamiltonian actions on symplectic manifolds Foucault categories. So if G acts in a Hamiltonian manner on a symplectic manifold X omega and X is compact, then the action is locally trivial. Action on the Foucault category of X is locally trivial. If X is not compact, depending exactly what you do at infinity, you may just get that, but maybe 2 examples would be helpful. There are actually 2 examples of what I just said. Some example. So G acts on X, which is now just a smooth manifold. Then, of course, it acts on the Durham complex of X by, well, geometrically. And the infinitesimal action is trivializable in the following sense, that L psi is the infinitesimal action, so the algebra action, the vector field action, is a commutator. So this gives a trivialization, gives an infinitesimal trivialization of the action. Oh, the action is on an algebra, but let's say it acts on modules over this, the category of modules. And this action is not locally trivial. Because modules of a Durham complex are the same as D modules, roughly. And if you take a skyscraper D module at a point and you move it by a group element, that's not isomorphic to the original. You can only move infinitesimally, but not globally. But there's, of course, a way to fix that. But if you restrict to G monodromic D modules, then it is. And G monodromic means that the connection on the D module is integrable in the orbit directions. So connection integrable. So for example, flat vector bundles. Orbits. And the first example is what you get from the Foucault category of the cotangent bundle according to Nadler and Zaslow. If you don't, well, I guess with infinitesimal wrapping they call it, if you don't perturb the Lagrangians at infinity. And that's a non-compactness feature. So non-integrability of an action of a Lie algebra comes from a lack of finiteness somewhere. All right. What are we doing? Ah, yes. Time to tell you finally something about the torus and then state the mirror symmetry for the torus, I think, and then, yes.
So you said if G acts on the symplectic
By Hamiltonian fashion, a symplectic, compact symplectic manifold, then the action on this is locally trivial, assuming we believe some very basic properties of the Fourier category. So
is this I don't know. You mean this is a theorem or
well, it's a theorem, I guess, whenever the basic I'm not sure if there's a packet of standard conjectures in the Fourier category, but for example, there's a standard conjecture that the Lagrangian correspondence gives a functor between Fourier categories, which is proved, I think, now maybe in the monotone case. Not sure the latest is. Woodward and Warhammer are working on that. So when that holds, I think then you can show that. I mean, the thing that you need to know is that a Hamiltonian motion of a Lagrangian local system on it produces an isomorphism between the source and the target in the Fourier category, quasi-isomorphism. Actually pins one down. That's the lemma that's needed. So let's say if this is not true, then something's seriously wrong with the construction of the Fourier category. I mean, it's meant to work. Meaning you cannot do almost anything with it, that sort of thing. And compactness means, well, you see the necessity of the condition here. All right. But I think in any example you can actually compute the Fourier category of some variety you like. You'll see that it's true because you'll see in the toric case how we'd write the action. But I'm not the person to ask about Fourier categories, you know. I defer such questions to Denis or any other volunteers. Uh-oh. Broke it. So let's describe very concretely first, and I'll write in more general, what happens for the torus. So a little theorem, it's an exercise almost. So little theorem is locally trivial. So T is a torus. It doesn't actually matter if it's complex or compact here. Locally trivial actions of T on C are the same as, really are the same as, homomorphism ring, let's see, E2, be safe, ring homomorphisms of the group ring of pi 1 of T into the Hochschild zeroth, the center of C, a zeroth Hochschild cohomology, endomorphisms of the identity functor. And now the Langlands dual group comes in for the first time. This is, of course, the space of polynomial functions on the Langlands dual torus. So these are polynomials. So this is group ring notation. My notation may be confusing. These are functions on T check. So if you have such a thing, you say that the category C is fibered over T check. C is fibered T check complex this time, and these are polynomial functions, just so, well, that is a notation. Fibered over T check. And with some mild conditions, such as C is closed under co-kernels, which is something you usually want, you could again restate it by saying that C has a structure of a module category over a tensor category of coherent sheaves on T check. So C is a coherent sheaf on T check. Actually, let me say it differently. Modules with tensor product module category. And the little proof, the little theorem is little proof. So have T action, but now the exponential of the Lie algebra T maps to T with the kernel being pi 1 of T. The action was locally trivial, so it's trivial in the neighborhood of the identity in this vector space, but then you can continue to trivialize without any obstruction because it's contractible. This can be trivialized. So actually this carries no information, but on pi 1 of T you have two trivialization, one because you've just constructed it, and the other because pi 1 maps to 1 here, and the identity goes to the functor 1. So you get a group homomorphism from pi 1 of T to the automorphisms of the identity functor on C, and that's the same as a ring homomorphism from the group ring generated by pi 1 of T to the endomorphisms of the identity functor, which is what we have. Okay. That's the structure. Automorphism of the identity functor, so, well, it's a zero social cohomology, but it means you have a functor sends x to x, and this is the identity, and the automorphism of that. So for every x, you want an ax in auto of x, and this must be central. In other words, it must commute with all morphisms. So you have an x, and the y, and an arrow, and here you have ax, and here you have an ay. Then it's an obvious condition. So this is essentially nothing. Just from a definition, this is what it means to have a model or locally trivial action of T on a linear category. And now let me explain where this comes from. This is a mirror symmetry from A to B direction for C, and it's also a categorified Fourier-Mukai transform, or categorified causal duality, or there are a million other ways to rediscover it, because after all, for a billion Lie groups there isn't so much going on. But let's write some examples. This. So mirror symmetry between BT and T check, and first it's going to be A model BT, B model T check, T check, and I would say integrable, just to specify, I would assume the action was locally trivial. So from a category C, you send that to the sheaf of categories over T check, which gives it spectral decomposition in other words, the points of T check are the, so actually I said that earlier, so that's obvious from this, that in the case that I forgot that, I'm sorry. When C is vect, it's obvious what this is. E.g. C is vect. Then of course this is just C. So we're looking at representations of pi 1 into C star. And these are the same as points on T check. And actually those points are the fiber functors for the category of coherent sheaves. So one-dimensional locally trivial representations of T are the points in Langlands dual torus, and actually that's the definition of the Langlands dual torus. So T check is the categorified Pontryagin dual of T. Which is just the space of one-dimensional representations with tensor products. So it's a group of one-dimensional representations. T locally trivial. Reps. So this is a spectral decomposition when you sheafify it on T, and in the other direction, from a sheaf of categories, we take its global sections. That's a category. Sections. And some examples. So C of functions on T check, such here, functions on T check as a module over itself. Global sections, functions on T check, and this I claim has a T action, T lock action. I'll have a minute to explain to you what it is. Then a point or fiber functor, vec tau, tau is in T check, the point in T check complex, sorry, is just vect with tau action. And it is something I definitely won't have time to explain. Vector delta, which is a Casimir twisted fiber functor, is a mysterious one-dimensional representation of T, which hasn't shown up yet. You have to ask me over beer what it is, because I just want to suggest what's going to happen in an abelian case, and we'll have to close with that. And let's write the other side as well in this case. The other side is B model BT. These are categories with T action, which is not assumed to be locally trivial. So the other side is integrable A model for T check. And that means locally constant sheaves of categories. And in this, if you trace the correspondence, you get, well, there's an action of T by translation on the category of modules or sheaves over the group itself. And this corresponds to a category of local systems of T check, or log T check. It's all local systems. Well, there's more stuff. The one-dimensional representation vect corresponds to local systems of T check pushed down to T check. So sort of the universal covering. The sheaf of categories coming from the universal cover. So it's a sheaf of categories with fiber rep of T check. And, well, we can go on, but let me just tell you the general rule since I mentioned it. I do have one more minute, right, from the delay time, I hope. Yes? No? Good. I'd like to finish. Oh, chop. So, fact on dt cross T check with a flat connection, so let's say locally trivial. There is a Poincaré gerbe. There is a canonical class, in other words, an H2 of this guy bt cross T check modulo locally trivial coefficients in O star, sort of de-looping the Poincare bundle once. Same on BT, locally trivial across T check. There is a Poincare gerb. And the mirror symmetry I wrote on that side. Mirror symmetry is the Fourier Mukai transform with respect to that. And I should say to get an equivalence, here there are conditions. Conditions on C needed. Something along the lines that's a coherent sheaf of categories. So I'm not going to explain some examples of mirrors. It's too bad, because that's the interesting part, that examples actually work. Let me just say one word about non-abelian case, so I don't then just give you the wrong statement. So non-abelian G. So the little theorem becomes that the locally trivial G action on C, category C, is the same as an E2 homomorphism from the homology of the base loop space of G into the Hochschild homology of C. And the connection, the Langlands dual, goes back to a theorem of Bezrukavnikov, Finkelberg and Merkovich. Which says that spec, you won't see it if I write it here. Last sentence, I promise. That spec of that ring, H star of omega G in C, is the exceptional fiber over 1 in G check of a blow up of the cotangent bundle on the space of conjugacy classes. Of a blow up of the cotangent bundle of G check mod G check. Conjugation is a singular space, of course. And specifically, this is the GIT quotients of complex. The GIT quotient of a regular part of the cotangent bundle, holomorphic GIT quotient, algebraic GIT quotient by algebraic symplectic quotient, I want to say, sorry, by GC conjugation. So in other words, the story doesn't happen actually on the space of conjugacy class, but inside its cotangent bundle, and it's sort of concentrated near the identity of the group or on the exceptional fiber over the blow up. And of course, I'm already over time, so no chance of explaining that. Thank you. Yes?
G is a finite cyclic. This is, I mean, like Jarvis Kimura computation, like 2000 was a good example of what you're saying. G is a finite cyclic.
Yes, there's a good example which I probably didn't write on the list, that if you have, I forgot on which side now, if you divide by the torus by a finite cyclic group, it's something that's well known in mirror symmetry, it's very obvious. If you take a covering of T check by a finite group F, so I think before I had said that local systems on over T check corresponded to, what did I say, coherent sheaves on T.